Hello, in this video, I would like to explain about the sampling distribution of the sample mean. Let us consider a population which has the mean mu and the standard deviation sigma. And let us draw a simple random sample of size n from this population, the population which has the mean mu and standard deviation sigma. If n is large, if the sample size is large, then the sampling distribution of the sample mean, what we have drawn from the population, will be approximately normal with mean mu and standard deviation sigma by square root of n. That is, if X is a population with mean mu and standard deviation sigma, if n is large, the sampling distribution X bar will follow a normal distribution with mean mu, standard deviation sigma by square root of n. If we are considering the central limit theorem, then regardless of the shape and regardless whether it is discrete or continuous, it can be a discrete function, it can be a continuous random variable, it can be symmetric and non-symmetric, whatever it is. If n is large, then the sampling distribution of X bar will definitely follow a normal distribution with mean mu, standard deviation sigma by square root of n approximately. On the other hand, if the original population is normal with mean mu, standard deviation sigma, if it is normal, then automatically the sampling distribution of X bar will be normal with mean mu and standard deviation sigma by square root of n. If the original population is normal, automatically the sampling distribution will be normal with mean mu, standard deviation sigma by square root of n. If the original population is from any distribution, it need not be normal, it need not be continuous, it need not be discrete. If it is any distribution, but if n is large, then the sampling distribution will be approximately normal with mean mu, standard deviation sigma by square root of n. This is what the central limit theorem says. So when we think about the central limit theorem and otherwise, see, if you have a population with mean 64.5 and standard deviation sigma equal to 2.5, then you'll have a flat curve, flat bell-shaped curve, which describes the population, the original given population. So that is a population distribution. So depending on your n, say n is 32 or 35 or 50, accordingly, the sampling distribution will follow a normal distribution with the same mean. So the center is going to be the same, but how it is spread, the standard deviation is not going to be sigma, which is 2.5. It is going to be sigma by square root of n, which is 2.5 divided by, say, square root of 35, or 2.5 divided by square root of 50, whatever n you have. So when you are dividing by n, naturally, sigma by square root of n will be much smaller than sigma. When you divide by square root of 32 or square root of 50, the 2.5 by square root of 50 will be definitely less than 2.5. So the resulting bell-shaped curve, which describes a sampling distribution, will be a narrowed one with a high peak. It's like the green bell-shaped curve what we see in this diagram. And in this case, most of the values will be clustered towards the center. Whereas the other one, the population distribution, will be widely spread, whereas the sampling distribution is the narrow curve, the peak curve, what we see here. Let's take this example, and we are trying to find the heights of male students. Assume that the heights of male students in a campus is normal with mean 70 and standard deviation 2.8. If we are choosing only one student at a time, we are trying to find the probability between 69 and 71. So you have the bell-shaped curve, and we are trying to find the area within this 69 to 71 area under the curve between 69 to 71. So if we are using the standard normal curve, we cannot make use of that 68, 95, 99.7 rule in this case because it doesn't coincide with this. The standard deviation is 2.8, doesn't coincide with -1 sigma, 2 sigma, 3 sigma. So let's make use of the standard normal probability table. We have to find the z-score value. In order to standardize that, we have to find the z-score value. The formula is x minus mu by sigma, where mu is 70 and standard deviation is 2.8. So for 69 and 71, we can find the corresponding z-score value, z values, which are negative 0.36 and positive 0.36. So if we are interested in finding the probability between 69 to 71 for x, that is the same as the probability between negative 0.36 and positive 0.36 for the standardized variable z. So using the table, we can get the area below 71, that is area below 0.36 is 0.6406. And the area to the left of negative 0.36 is 0.3594. So the area between 69 and 71 will be the difference between those two, which is 0.2812. The same results can be obtained using our graphing calculator. If we want to use our graphing calculator, we have to use the key normal CDF. We can find the normal CDF using the second variables, which is the distribution. Under that, we select number 2, which is our normal CDF. In our normal CDF, we have to use the lower bound of that region, upper bound of the region, whatever we find, and the mean standard deviation. In our case, the lower bound is 69. Upper bound is 71 because we are trying to find the area between 69 and 71. So L is 69, U is 71, mu is 70, and sigma is 2.8. When you plug in these values in your calculator, you get that as 0.2790, which is approximately the same thing as what we got in our table, using a table. Let's take the second part of this question. If measurements are made on 32 different students, so it is not on one student, we have a sample of 32 here. Your n is 32. You're trying to find the probability that the mean height of these students will lie between 69 to 71 inches. So in this case, we are looking for the sampling distribution, which is a peak curve, where the area lies between 69 and 71. So we would like to find the corresponding critical value z star, which is x bar minus mu by sigma by square root of n, where mu is 70, sigma is 2.8, n is 32. So when x bar is 69, we can find the value for z star, which is negative 2.02. For when x bar is 71, you can calculate the value for z star, which is 2.02. So the probability of this 69 to 71 of x bar, that is the area of this bell-shaped curve, which describes a sampling distribution between 69 and 71, is the same as the probability of the standardized normal curve for the z star between negative 2.02 to positive 2.02. Again, using the same standard normal probability table in our textbook, we can find that this is nothing but the difference between 0.9783, which is the area below 71, and 0.0217, which is the area below 69, and your answer is 0.9566. We can find the same result using our graphing calculator. In our graphing calculator, we can just use the normal CDF, the lower bound and upper bound of this, the mean of this bell-shaped curve, and the standard deviation of this bell-shaped curve, which is 2.8 divided by square root of 32. And you will get the same answer there like the previous one, what you got in your table, as 0.9566. So this example gives us an idea of how to calculate the probability for the normal curve and the sampling distribution, the bell-shaped curve, the peak curve, using the central limit theorem. If it is not a normal curve, even if it is any curve, if n is large, we can make use of the same idea and get the corresponding probability between the two variables. Hope this video was helpful. Thank you for watching. Thank you.